Swayam Prabha. Digital India. Educated India.
Good morning. We have started our discussion on various aspects of transition and turbulence, and what you are looking at there is the course content, and we have been basically talking about how historically the subject has developed. So, let us get back there, and historical introduction that we have been talking about, that following the experimental observation of Reynolds, which was in turn triggered by the observation by Stokes that he could not get the pipe flow calculations to match with the experiments, was followed by Reynolds in his pipe flow experiments, where he showed that the small ambient disturbances actually magnify, and that leads to the settled laminar flow to go from laminar state to turbulent state, and the whole idea of that experiment will be revealed to us later. But let us now basically talk about the other aspects, that the whole stability study was started with the mistaken belief that viscous action, if it is there, it only damps the disturbances, and this was essentially the idea of Kelvin and Rayleigh. This was settled after a lot of jousting, you can say, between various groups, among various groups from Germany and Europe in the continent, as European continent in UK, and finally settled by experimental observations at NBS Washington by Dryden's group. And we concluded that it kind of established the existence of wavy disturbance flow at the onset, which we called as Heisenberg-Tolman-Schlichting waves, or HTS waves, which was obtained by linearized stability theory for a parallel flow. That is the catch. However, when the same theory was applied to pipe flow, channel flow, and Couette flows, it was seen that these are unconditionally stable for all parameter values. So, basically then people started looking at alternate explanations, and they suspected that this could be due to the nonlinearity of the instability regime, or it could be that we had used a assumption that the streamlines are parallel. That could be at fault. So, basically we have to include the growth of the boundary layer into account. That is what we mean by non-parallelism, and of course, we may have some kind of a other unknown mechanisms, and in this context we come to the work of Markovin, who in 1959 espoused what is called as a bypass transition. Bypass transition is that scenario which actually occurs without the presence of this waves, that Heisenberg-Tolman-Schlichting waves that we talked about. And he also kind of followed the experiments of Schubauer and Skramstad, where it was noted that all kinds of disturbances do not lead to instabilities. You have to be pretty selective. So, what was observed by him, that the flow itself has a property called receptivity, that it is receptive to certain class of disturbances. It is not receptive to all kind of disturbances. So, receptivity is something that was what was proposed, as opposed to the general theory of stability, which is posed as an eigenvalue problem, And as you know that in all eigenvalue problems, you do not need to define what is the disturbance, right. You have a homogeneous differential equation, you also have a homogeneous boundary condition. So, you have no way of putting in this information that there is some definitive input. So, basically this is the beginning of a dynamical approach of study of stability through this receptivity analysis. So, in the receptivity analysis, what you do is you look at the dynamical system, so that is acted upon by some input, and that leads to observable outputs. Okay. And so, receptivity is the property of this dynamical system. Receptivity is the property of the dynamical system, and this property is what we call as the transfer function. So, in a sense, what we are talking about is that the output is nothing but a kind of a product, which I will use a scientific term called convolution of the transfer function times the input. This is important because you see, as long as we cannot include what is causing the perceptible disturbances, the picture remains incomplete, and this is what Markovin was suggesting, that we should talk about it. So, if this transfer function is not receptive to that class of disturbances, then even in the presence of that input is not going to do anything. This is rather important, because when Schumacher and Skramstad in their experiment in the tunnel tried to basically excite those waves by acoustics, and they were not successful. Then they used a kind of a vibrating ribbon. So, what they did was the following, that if you have a, let us say, a flow past a flat plate, then the boundary layer grows like this, and what they did was they put in a kind of a vibrating ribbon here, which is close to the boundary, and then started vibrating it. Okay. So, this is what you may call as the vibrating ribbon. This was made of bronze, and it has vibrated at some specific frequency, which was actually used in Tolman and Schlichting's calculation. We talked about in the last class that G. I. Taylor also wanted to do some experiments. What G. I. Taylor did was this: you have a plate, and then you put in a kind of a vibrating bump. So, this is like a circular patch, flexible, which goes up and down, and this was the experiment that was conducted by G. I. Taylor in 30s, early to mid 30s, and this was the experiment that was done by Schumacher and Skramstad. This was published in 1947, but it was done long time before. It remained classified during the war years, and it got published afterwards. So, this vibrating ribbon was excited at frequencies of, let us say, 50 to few hundred hertz. Whereas, in this case, this was vibrated at 2 to 5 hertz. So, this could not produce Tolman-Schlichting wave, but this could. The reason is the eigenvalue calculations of Schlichting did show that the flow is not receptive at low frequencies of this kind, but they are indeed receptive to this frequency. And this was something that one needs to do. In experiments, you just do not simply do a qualitative experiment and then say make value judgment. So, we understand. Although I must tell you that G.I. Taylor was an outstanding fluid dynamicist of his time. It is said that he never took any sponsored project. He used to do science for its own sake, using his own money and resource, and he was a professor at Cambridge. So, he never did any sponsored research. So, he used to do it for the love of the subject, but at the same time even the person of that caliber can also sometime take a wrong step, and here is an example. So, this was something that was very good that Markovin suggested that we should look at the receptivity approach. So, we need to understand the transfer function very clearly. Stability theory only looks at the transfer function, whereas receptivity studies looks at this full thing, because that also includes the information of the input. Okay. We mentioned that there were something like some flows like Couette flows, pipe flows, which does not show linear stability. So, what happened is some researchers commented that those flows actually undergo transition because they suffer transient energy growth via some modes, which they call as non-normal. Well, we will go through these details. The eigenvalue analysis looks at one frequency or one wave number at a time. So, those individual frequencies or wave numbers are called normal modes. So, here these people are talking about some kind of a energy growth, not growing like a wave, but it is growing like a in time, okay? And that is transient. It just grows and then it is not there. I mean, it directly takes the flow from laminar to turbulent state. So, it is not like a gradual growth that you associate with the Heisenberg-Tolman-Schlichting wave transition route. Okay? Maybe this is a attempt to explain one particular type of bypass transition. We define the bypass transition as that transition which bypasses the wave and its growth. Okay? So, this was that, and this is the view proposed by Trefethan and his colleagues in this paper. And there were other attempts by Landau, where he and his colleagues talked about algebraic growth of disturbances and interaction of different types of instability modes, etc. We will talk about this. Now, we also note that some researchers identify that you get fully developed turbulent flow due to some kind of a self-sustained instabilities. Means what? That you do not have to do anything, it will just become unstable, it will grow, become turbulent, then it may decay, but then again another set of disturbances will pick up. So, that process is self-sustained. Okay? And they said that during this process you create some kind of a distinct structure, which has been called as coherent structure. It is like, think of eddies, vortices. So, they are talking about some vortices or eddies forming, and those are what are called as the coherent structures. They have been seen actually in various experiments. Some theoretical analysis done by proper orthogonal decomposition or wavelet analysis also shows presence of coherent structures, right. So, this is precisely the status now. We are now in a time where we see that there are the possibilities that you have this transition taking place to the growth of waves, or you can have bypass transition, and bypass transition is basically a basket. So, it has many routes. We have talked about couple of them. One was the transient energy growth, another was algebraic growth of disturbances. There could be multiple instability modes interacting, and those also need not necessarily show you waves. But let me add at this point in time that this experiment that we talked about was a very specially designed experiment, and this ribbon was excited at a fixed frequency. So, what we are doing? We are creating a monochromatic wave, right. So, we create a monochromatic wave and we see some kind of waves that grow downstream. Now, what happens in the immediate vicinity of the exciter is not talked about a great deal before 1990s. People used to think that that is not important. Even you will see some of the books or monograph, they actually erroneously show as if that there is nothing up to here, and all of a sudden you start getting some finite waves growing. That is a wrong picture. In fluid flow, especially at low speed, you cannot have such kind of a discontinuities. You will see that it has to be a smoothly growing solution. In fact, when we first did all this receptivity calculations, we identified two distinct components of those solutions. One we call as the near field, which is in the immediate neighborhood of the exciter, where we are exciting the flow, and a far field. In the far field, you see those waves, HTS waves that we talked about, but in the near field, you may see some kind of a totally different structure. We will talk about it in greater detail. Okay. So, this is the picture that we see. Now, let us go through the formal description of the subject through this introduction. What we see as instability in fluid dynamical flows, they are there always, right. That is what we say, that they are ubiquitous, and even today they remain as challenge, because we still do not completely understand transition and turbulence. We understand bits and pieces, and we are also going to do that. However, we will try to integrate the whole thing together, and as you can see that you have a laminar flow, then you have a transitional flow, and then you have a turbulent flow. In this course, we will try to go from the laminar flow side to that side. We will not put the cart before the horse. We will not talk about turbulence, and then we will say make some assumption. Most of the time, people who actually spend all their effort in studying turbulence, at the back of their mind, they basically think about some kind of a universality of turbulence. What it means is, irrespective of whatever input you have, the eventual output you will get only one turbulence, right, one kind of turbulence. Although they describe it not in a deterministic manner, they describe it in a stochastic fashion, but they say that in a stochastic picture also you have a universality, which is debatable and which we do not agree, some of us do not agree. So, that is why what we do is we go from the laminar flow side, first it becomes unstable in a primary mode, then that you could have a secondary instability, then you could have tertiary instability, you could have nonlinear stages, and then you have fully blown turbulence, right. So, that is what we are talking about. So, you know, for pure fluid dynamical flow, we are saying that it is they are everywhere, but if you add some additional parameter, I mean physical events into it, for example, if we add heat transfer or if we add chemical reaction, as you may see in a engine, those also suffer instabilities, and those instabilities are going to be even more complicated, right. So, we will probably spend some time talking about heat transfer. Chemical reaction we are not going to discuss at all. And of course, we are going to emphasize various theoretical computational developments. We will talk about experimental results, how experiments have to be designed. This is an example that you want to see something. If you are not careful, you end up doing this kind of experiment instead of this. So, experimental approaches are also important. So, if you are going to work as a theoretician, it is necessary that you communicate to your friends who will do those experiments, and you should tell them how to design the experiments. This is rather important. Okay. So, let us talk about one of the application that should motivate most of you, where this understanding of the flow transition is very, very crucial. For example, we are talking about modern day aircraft, where we basically want to keep the flow laminar as long as possible. Why? Because of the reason that if I plot let us say the drag or one component of it, the skin friction versus Reynolds number, then we know even for flow past a flat plate, the laminar flow, if I do it in a log scale, laminar flow, it goes like this. So, this is the CF versus the Reynolds number for laminar flow, and then depending on the kind of disturbance that you have, it actually goes on to a turbulent branch. So, the way the transition process takes place depends on the background disturbances, and it connects like this, it connects like this. So, depending on different levels of disturbances. So, that is why the receptivity factor comes in. Where would you continue up to this laminar flow? Depends on how you control the disturbance environment. If you can control it well, then instead of flow becoming turbulent here, you can delay it and it can happen later. And you can see that we are talking about a log scale. So, if I look at a position, then I can see for laminar flow the skin friction is here, and for the corresponding turbulent flow, if it is fully developed turbulent flow, it is there. This difference is quite significant. We will give you an example. You find that this is significantly higher. So, one of the goal for any good aircraft designer would be to keep the flow laminar as far as possible. And there is a technology which is called natural laminar flow technology, which tries to alter the wing geometry such that you can control the transition process. Okay. So, that is those wings are called NLF wings or natural laminar flow wings. And you understand also that in designing those wings, we are not depending upon active devices, right. Why not? Because for active device, if it does not work, then we will be in deep trouble operationally. Think of that you have designed an aircraft thinking the flow will be laminar. So, you have put in some engine, and then up there in the sky while it is flying, your active device fails and flow becomes turbulent and engine does not have sufficient power, then your flight is in jeopardy, right. So, in aerospace engineering, we are always very conservative. We always try to go for passive device instead of active devices. Although that does not preclude that we do not basically look at active devices. Lot of researches goes on using various active devices, and here I have shown you a picture of a Airbus 340. So, this is the isometric view of that aircraft that you can see. The green part of in this diagram indicates where you could try to keep the flow laminar. So, you are not trying to keep the flow laminar over the full wing. It is only part of it you try to keep it. Okay? And if you can do that, one is talking about 12% gain, 12% reduction in drag, and that is quite significant. And as I told you that apart from the fuselage, most of the aircraft actually experiences drag that is due to skin friction, the viscous action. It is not as much as due to the pressure component. We have two components of drag, skin friction drag and the pressure drag. So, it is the fuselage actually that gives a significant amount of pressure drag. I will give you an estimate. So, you will see that estimate. So, you can actually think of reducing the wing drag by 10 to 12%, and that is quite significant. Empennages are those control surfaces, right? The horizontal stabilizer and the vertical stabilizer, they are also wing like bodies. So, you could basically keep the flow laminar over those also. Whatever works in the wing, they would also work in the horizontal and vertical stabilizer. In addition, you could also keep the flow, part of the flow over this nacelle, which houses the engine laminar, and there you can think of getting a 1% reduction in drag. So, basically it is quite possible to do that, but you notice that this aircraft, the wing is swept back, right. It is making some angle with the fuselage direction. So, that swept back wings are not too amenable for keeping the flow laminar. That becomes better if you have the sweep back angle smaller. That is why you will see many of the aircrafts that people are thinking of designing, they would not like to have the sweep back too large. A rule of thumb is try to keep your sweep back angle less than equal to 20 degrees, then that should be okay. Why do we need sweep back? Most of these aircrafts fly at what speed? Do we know it is about 0.8 and thereabout. So, if the aircraft is moving at about at a Mach number of 0.8, then in some part of the wing, then you could get a shock. So, the good news is if you can keep the flow laminar and design the contour in such a way, that also helps in controlling the shock. So, those are called supercritical wings. Supercritical wings are designed for keeping the shock weak. Okay. It so happens that what works for supercriticality also works for natural laminar flow. So, all this aircrafts that you see, modern day aircrafts like A340 or Boeing 757, 767 and the higher models, they all have NLF wings, which are also supercritical wings. So, you try to push the frontier, you try to go as high as possible in terms of Mach number, okay. And to avoid shock forming, you have to provide the sweep back, right. So, what matters most is the Mach number normal to the leading edge, not parallel to the fuselage. Okay. So, that is why you sweep it back, so that the Mach number normal to the wing becomes lower. Okay. So, that is the whole idea. Now, if you are trying to design a new aircraft, these are the problem areas. Even today, we do not predict transition very well. We simply do not, and even if we do, they are not very reliable. And if you are talking about problem of prediction, experiment is virtually impossible. It's simply because of the fact that every wind tunnel brings its own signature. You take the same aircraft model and do experiment with 2 different tunnels, you will find a very disappointing result, because they will be all different. Okay. So, this is what we try to keep in mind when we go along. So, we are going to look at how things work, and this is an example of a beautiful design. This is I am not very sure if it is still out yet. It was supposed to have been inaugurated this year. This is an aircraft designed by Honda, and you can see unlike any other aircraft, the surface finish of this aircraft is superb, and this has happened. The automobile sector, they have better manufacturing ability than what we do in making the airframes. If you come close to an aircraft, you see those rivets, the gaps, they look very ugly, and they also actually create a big potential for transition. Whereas, these people have designed the wing as a NLF wing, Honda. I will show you some clip today itself. And not only that, they have also positioned this nacelle with respect to the fuselage in such a way, it is a beautiful design, because if you calculate the drag of the nacelle, you calculate the drag of the fuselage, add the two up together, and then you go to the tunnel and do the experiment with the fuselage and nacelle together, that total drag is lesser than the sum. So, this is what is called synergy, right, in design. So, this is one of the most beautiful aircraft that has been designed. We have studied it to some extent. I will show you some of the work that is done by Yogesh here. You will see some of those calculations. Now, I was telling you what is the actual scenario. Now, this is the scenario. On the left hand side of this table, we have shown you if the flow condition was fully turbulent, okay, at all surfaces. And what happens is the aircraft designers talk about the drag in terms of counts. Okay. So, for example, the wing contributes a drag component which is 0.0060. Okay. This is a drag coefficient. So, it is a non-dimensional number, we will define it, but let us get the relative idea. Compared to that, you can look at the fuselage that contributes to 0.0092. So, you can see it is the fuselage which actually contributes more drag than even wing. Then the stabilizer gives you a drag of the order of the value of 0.0027. So, roughly about half of what you get from the wing. So, it is not negligible, right. And look at the other nacelle and other miscellaneous contributions, that is about 0.001. This all adds up to I think 0.0189 or something. Okay. And this column tells you the percentage component. So, wing drag is roughly about 32%, the fuselage is about 48 to 50%, and the empennage contributes about 14-15% drag, and the nacelle and other quantities define about 5 to 8% of drag that we talked about. Now, if I showed you that picture where we shown for the Airbus 340 A340, and suppose we manage to keep the flow fully laminar on all lifting surfaces, not part, lifting surfaces. So, lifting surfaces are just the wing and the empennages, nothing else. So, if we can keep that, then you see the drag of the wing would come down from 0.006 to 0.002, right. So, that is a 1/3 the value, that is what we shown here. So, actually this jump for a flat plate is about 5 to 10 times. So, you try to keep the flow laminar as far as possible, and further you keep it, you can see the dramatic growth. So, suppose it becomes turbulent here, then this differential is not very much, but if you can keep it like this, so you can actually get a very, very significant reduction in drag. Okay. So, that is what you see, that the drag becomes 1/3 for the wing. Now, fuselage of course remains the same 0.0092, and the empennages also become almost 1/3, and other things kept as it is. So, you see the drag has reduced from 0.0189 to 0.0131. And now, you see what has happened. The wing contributes about 15% of the drag, but the fuselage contribution has gone up to 70%, and the empennages have also come down, and the nacelle has also come down. So, however, we have seen in that picture what the current thinking in Europe is, that you are not going to get fully laminar flow over the whole lifting surface, you are going to get part of it. So, this is an optimistic picture what would happen if you could do that. So, talk about let us say the flow over a nacelle. Now, there also people have done something. You see, what really matters is the pressure gradient in the flow. So, if I just simply take a cylindrical nacelle, then its pressure distribution is given like this. So, you have a suction peak here, right. So, following the suction peak, you have a severe deceleration of the flow, right. adverse pressure gradient is very large in this part, that actually triggers transition immediately. So, one rule of thumb is avoid adverse pressure gradient as much as possible. Okay. If you guys are aware of this NACA 5-digit series and 6-digit series aerofoils, those are designed, they knew about this, that you have to keep the flow under favorable pressure gradient as long as possible. And one of the theme in the development of those aerofoil sections in 1920s and 30s was to keep the maximum thickness point as aft as possible. Okay. So, they did push the maximum thickness point to say 35% to 50% and so on and so forth. So, that is the story of 6-digit series aerofoils. So, here also you can do the same thing. Now, you can see the contouring. Instead of having a flat diameter, now it has been increased, and if you are looking at flow less than Mach number 1, then such a contour would create a flow acceleration up to the maximum thickness point. So, you get a very smooth CP distribution as compared to this peaky CP distribution. So, this is one of the way people have been talking about reduction of drag over nacelle, and we have already said that it accounts for about 5 to 8%. So, whatever you get, it is good enough. Somebody said sometime ago that if you can reduce drag by 1%, the drag actually comes down, the operational cost comes down by a few $1 billion. Okay, we just saw that for a aircraft like Airbus, people are talking about some amount of drag reduction by promoting laminar flow, but we also saw the Honda Jet, which look gleaming and which has a very fantastic drag polar, which is very good. I told you about surface finish. Now, surface finish is not something that you only see with your naked eyes. Sometimes you would also worry about the roughness, which you can only measure using profilometers, right. So, those effect of even the small scale roughness could be very profound, and people have known about it, and this effect of roughness is a function of Reynolds number. You see all those NACA 6-digit series aerofoils which are designed, they somehow work for gliders, but they do not work for powered aircraft. Why? Because those unpowered aircrafts go at a smaller speed, so Reynolds numbers are lower, of the order of few 100,000, whereas even if you look at that business jet that we saw, Honda Jet, the cruise Reynolds number is something like 10.3 million, right. So, the aircraft that we have in our flight lab, they would also have a cruise Reynolds number of the order of few millions, if not 10, it would be few millions. So, at those high Reynolds numbers, the small roughnesses act like an amplifier. They really promote turbulence, right. So, effect of roughness on airfoil section is quite well known. That is why 6-digit series aerofoils are not used in any commercial aircraft that you would see. They have major effects on lift, drag and bypass transition near the leading edge. Now, let me tell you somewhat about the property of this natural laminar flow aerofoils. They have the following property, that if I plot the section property on this side, I will plot non-dimensional lift coefficient, and on this side I will plot the non-dimensional drag coefficient, and this NLF aerofoils or the 6-digit series aerofoils, those are designed in 20s and 30s, they have this following type of properties. So, what happens is you design it for say point here. So, this is your design point. So, at the design point your drag is quite nice. Okay. So, this could be your cruise configuration, but suppose when you are landing or taking off, or if there is some other off design condition, you can see that if you are here, then this drag and this drag, they are quite different. And roughness actually changes this curve altogether. If you have roughness, you could see that this could actually go like this. So, this is what is called as a drag bucket. So, most of those 6-digit series aerofoils have a drag bucket. The drag polar looks like a bucket. So, if you are working in this region, it is all very fine. You are outside that region, drag increases very, very badly. So, that is why it was done. Whereas, the modern day NLF aerofoils would be somewhat something like this. So, it is not a single point design, it is a multi point design. You try to design it not only for cruise configuration, you also try to design it for, let us say, landing and takeoff and so on and so forth. However, we have seen that this rapid increase in drag is contributed by roughness for those 6-digit series aerofoils. Okay. And what it does actually, this roughness elements where it sits, it is almost like this, like a bump, and you create some kind of a streamwise vortices. So, vortices which are like helical structure in the streamwise direction, and those streamwise vortices actually create an instability which is called the cross flow instability, and it is basically inviscid in nature. So, you have no way of controlling. Okay. Inviscid mechanisms are the most vortices create some kind of inviscid instability, and they are going to trigger transition immediately. So, that is why you try to avoid having roughnesses. This was investigated by a group, Rajatsky's and his co-authors actually tested a 45-degree swept wing with this particular natural laminar flow section. This is what is called also the general aviation wing, GAW wing. So, that is the number code for it 0415. This is a 15% thick aerofoil, and they actually compared the location where transition occurred for the following 4 cases. You take a painted surface, okay. One would probably think painting is making it smoother, but still despite that, if you look at peak to peak roughness height, that is of the order of 9 micron. 9 micron is not too large, is not it, but even from a transition point of view they could be disastrous. Now, you could also machine polish the surface. So, you can bring down the peak to peak roughness from 9 micron to 0.5 micron, this is the RMS value. Okay. So, you can bring it down, but what works best in life is the individual ability to do it by hand. So, a hand polished surface actually brings down the roughness height to even lower values. Okay. And they also studied something like a bump here, a 6 micron isolated roughness element. And what you would notice that this kind of picture that you would see here, this is your painted surface. So, it is like taking a cut and looking at sideways, right. You can see those jagged nature of the painted surface, and this is all in we are talking about micron level variation, and this is what you get when you machine polish it to the right, and the bottom one is the hand polished one. So, you can see that these 3 are somewhat different, and although there is a problem with hand polishing, you can polish it better where it is the curvature is less. If you try to look at near the stagnation point, near the leading edge, there the polishing may not be as good as this, it would be slightly degraded, but still it would be better than machine polishing. So, even today lots of model making for transition experiments, one does take care of that, and this is what you get. This is the story of average transition location plotted against Reynolds number, and you can see this is your painted surface. Okay. And then if you do a first polishing which is about 0.5 micron. So, this is your painted, this is your first polish, and this is your final polish. So, fix your attention on a particular Reynolds number, you see the painted surface, the critical Reynolds number location is somewhere around here, about between 30 and 45%. So, if I look at let us say 3 million, okay, Reynolds number, I think this is 10 to the power 4, right. So, this is 10 to the power 4. So, 3 into 10 to the power 4, the transition is occurring somewhere around 32%. But if you go to that first polished surface, then it actually goes from here to here. So, that is about 50%, and if you do a hand polish, you can actually even take it even better, close to 60%. So, you can see that it is not trivial, that you are talking about keeping the flow lamina from 30% to all the way up to 60%. So, effect of roughness is profound, and what do we do when we do calculations? We always calculate uniform flow past a smooth surface. So, you understand why we do not do such well when it comes to computing also, because we do not have wherewithal to put this input into your computations. Surely some of us try to do, but rest of the people, especially those commercial packages, have no way of really even comprehending this problem. Okay, so, we understand what it is. So, if I summarize the effect of roughness, if I have isolated roughness like what we have shown here, induces a 3-dimensional effect via the streamwise vorticity, and the streamwise vortices actually creates a inviscid instability. Okay. You can prevent transition occurring early by cross flow instability if you remove this isolated roughness by proper surface finish, and hand polishing can really create surface finish up to 0.1 micron near the mid chord region and 0.25 near the attachment line. Attachment line is near the leading edge, right. So, there you have a curved surface, you can do better than that. Now, why we study, we have talked about enough about this. So, we know what we are talking about, but here I want to show you what Osborne Reynolds did. Osborne Reynolds performed some experiments, his famous pipe flow experiments. He noticed that the basic equilibrium flow is unstable with respect to the background disturbances. So, let us see what he did in his experiment. This is a sketch of his experimental facility. It is probably taken from some museum where it is displayed. And this is the pipe in the middle. I will show you a better sketch later, but do understand the pipe is here. Okay. The pipe entrance is through this bell mouth. So, the bell mouth is visible, and at the center of the bell mouth a die is injected. This is where the die is kept on top. Okay. And what happens is one notices the following scenario, which has been sketched here on the right hand side, that if the flow was completely laminar, the die injected in the center would remain and go through the pipe. But what actually happens is something like this. It remains laminar, then it breaks down to turbulent flow very rapidly, and then this die gets mixed up with the surrounding fluid. So, that is a signature of turbulence there, right, chaotic nature of the flow. Sometimes what happens is, if you do take some care, then you do not immediately go to fully developed turbulent flow. Instead, you get something like this. These are like what they call as puffs. Puffs or slugs. So, you get something like a puff of disturbances going. So, that is what has been sketched here. You see, it is like a smoke ring kind of a thing that goes one after the other, and this is what actually you see in the experiment. So, this is what happens when you have laminar flow. It does diffuse, the dye diffuses, but if it becomes turbulent, you get this. So, what happens is, here is a case where the transition has occurred rapidly. Here it is going to happen little delayed manner. So, this part of the flow starting from here till the end, we will call it as a transitional flow. So, this was the famous experiment, and if we look at it and recall what we see in the textbooks. In the textbook, it says that if you have a Reynolds number around up to 2300 or so, you can keep the flow laminar. Anything largely in excess of that Reynolds number, flow becomes turbulent. We have seen that in the experiment of Reynolds, he could keep it flow laminar for a Reynolds number of 12,830, and he had to do all kinds of things. One of the things that we have noticed is this bell mouth. This bell mouth, what does it do? Again, it is a incompressible flow. You are reducing error, reducing the diameter. So, you are basically imposing a favorable pressure gradient, or you are accelerating the flow. In the presence of favorable pressure gradient, the background disturbances strength comes down. That is how you do it. And unfortunately, the lab where Professor Reynolds used to work in Manchester, it was next to a main road. Those days there were no automobiles, but there used to be horse drawn coaches, etc., and they used to give rise to acoustic excitation. And that is why he used to come back and do those experiments in the middle of the night, and he could keep the transitional Reynolds number as high up to 12,830. And this we are talking about 1880s. Subsequently, I think Ekman did experiments, and he reported Ekman, Schiller, they did experiments, and they reported that they could delay the transition all the way up to Reynolds number of 100,000. Okay. So, this is something we must keep in mind, that disturbance plays a major role, and that is what we wrote, that input, if you starve the input of disturbances, the corresponding things will be milder. This is what we see. So, in summary of this experiment, we say that equilibrium flow, that is the laminar flow, if we have obtained it analytically, we only worry about these two things, right. A mathematician always likes to think in terms of existence and uniqueness of the solution, but that story is not complete, because even if you have shown that solution exists and it is unique, you may not observe it in nature. That is related to what Landau and Lipschitz have said very clearly, that the natural flow that you would see, they not only follow the equations of fluid dynamics, but they will also have to be robust enough to withstand all those background disturbances. They have to be stable, then only you will notice that flow, right. So, this is at the heart of instability studies, and we said that Reynolds could keep his transition Reynolds number up to 12,830. That prompted him to say this, that the condition that he could achieve is one of instability for disturbances of a certain magnitude, right. And if the magnitude is lower, then flow is stable. If magnitude is larger, it is unstable. So, what is this? This is the nonlinear aspect, where you have the phenomena depends on amplitude, that is nonlinear instability. This is something that he could prophetically say that, because we have said that subsequently after him, when linear theory came and people investigated, it was found to be stable. So, why pipe flow becomes unstable? So, Reynolds himself gave this suggestion. Okay? I think we will stop here.